Okay, so let us start today's session. We are very glad to welcome today Jacob Bedrossian, who is a professor at University of Maryland, who is an expert of deterministic and stochastic PDEs in fluid mechanics and plasma physics, who will be an invited speaker at next ICM in 2022 in St. Petersburg, and who will speak today on vortex filaments in 3D Navier-Stokes equations. It's up to you, Jacob.
Yeah, thank you. Thank you for the invitation and the nice introduction. Okay, yeah, so I'm going to talk about vortex filaments. This is joint work with Ben Harv-Griffiths, who's at UCLA right now, and Pierre Germain, who's at the Courant Institute right now. Okay, so just to remind, maybe I don't really need to remind people in this seminar, but just in case, I'm going to be talking about the incompressible Navier-Stokes equations, but mostly in vorticity form. So here in velocity form, U is a vector, just in case the notation is not clear. Pressure is a scalar, but we won't be talking about the pressure in this talk. And okay, so the curl of the velocity field satisfies this self-contained equation on its own. So all you have to do is solve this system. So given the vorticity, you can recover the velocity with this Biot-Savart law. And this nonlinearity has a really important structure to it. So it's basically the natural conservative transport for vector fields. So it's conservative not in the sense that it's just transported around like a scalar would be transported. It's conservative in the sense that the flux through a surface moving with the flow is conserved. So that's a fundamental conserved quantity for just this nonlinear piece. And this is a regularizing viscosity term. So the difference between the Euler equations and the Navier-Stokes equations is the presence of this viscosity. All right, so what is a vortex filament? So a vortex filament we observe in nature, and we can isolate in experiments and computer simulations all the time. So what they are, they're regions of vorticity concentrated along thin tubular neighborhoods. So you have vorticity, which is directed tangent to the curve, and so the fluid is rotating around it rapidly. Maybe the most recognizable example of such a filament is a tornado. Or similarly, if you have a sink and you unstopper the plug, you'll see a vortex form. This is a type of vortex filament. Other places you can see them are wingtip vortices. So here's a particularly like this picture. So here you can see the vortices trailing off. I think these are the air brakes. Here, and you can see, so it's nice. So not only, so the thing is the fluid is rotating so rapidly that it drops the pressure and condenses a cloud behind the airplane. But since it's flying through another cloud, you can actually see the rotation of the fluid around the filaments themselves. Actually, you can see these things from inside the airplane. If you're seated behind the wing, when you go in for a landing, sometimes if the conditions are right, you can see these filaments trailing off the edges of the wings and off the air brakes and stuff like that. This is a vortex filament in a loop, isolated in the laboratory in Chicago, which does lots of really cool experiments on vortex filaments. So these are very coherent structures. So you see them all the time in three-dimensional fluid mechanics, and they're transported with the flow because of this conservation of the flux through surfaces. So you can prove that sort of a line, which is tangent to the vorticity field, will always get transported like that as long as the velocity field remains smooth. So because we're talking about an extremely intense vorticity, it seems like the nonlinear term should dominate. So the viscosity term should be irrelevant. But actually it turns out that the width of the filaments are so small that viscosity should actually matter in the core of vortex filament. So it's sort of like at the large scale, we expect them to behave like the Euler equations. So we expect that the geometry, we expect that the curve should evolve with some kind of geometric evolution, which you could just derive just from the Euler equations. That's what you sort of observe, at least to leading order. Although the mathematical proof of such a thing is not quite not quite there, but that's what you pretty much expect. So what you expect is like the large scale dynamics of these filaments are governed basically by Euler, but the small scale dynamics should be governed by Navier-Stokes. So the dynamics near the core. The thing is, one of the difficulties in completing a mathematical proof that the curve evolves with some particular geometric evolution equation is one of the difficulties is understanding the stability of the core. So if the filament doesn't stay a filament, then you can't prove that it solves some geometric evolution equation. And so that's kind of one of the main reasons why we don't have a complete proof of these geometric evolution laws, because we don't really understand the dynamics near the core of the filament. So what we want to do in this work is study the filaments from the perspective of the Navier-Stokes equations rather from the Euler equations. And we want to let the viscosity naturally regularize the core. So we're going to start with an infinitely thin vortex filament. This is not our idea. This at least goes back to Giga and Miyakawa's work in '89, where they study vorticity, which is initially concentrated on some smooth curve. So you actually have a measure-valued initial vorticity, which is kind of like basically the one-dimensional Hausdorff measure of the curve, but with a vector along the tangent. So this is a very singular initial data. So in particular, the velocity field is not locally L2. So if you're familiar with fluid mechanics, you know these Leray-Hopf solutions, which you can generate from any locally L2, essentially any locally L2 initial data. But such things do not apply here at all. So you cannot produce any weak solutions with this classical theory. So instead, and in any case, we want to understand if the filaments are actually stable and coherent. So we don't want weak solutions for which we may have many different nonsensical or even many sensical weak solutions. Just because you have many solutions does not mean they're nonsensical. But we want to know if we have one solution. And so what we want to study are actually classical solutions, but not exactly classical solutions. So we're going to study the next best thing, which in fluid mechanics is called mild solutions. So we want to study vorticity in this form. Now, when you study mild solutions for semi-linear equations like this, as it turns out, the scaling symmetry of the equations plays a really crucial role. So it can be a little confusing here because sometimes we talk in vorticity and sometimes we talk in velocity, and the scaling symmetry is different. And so what you find is there are three types of norms that you might want to put. Let's say on the initial data, which is kind of like an L infinity in time and the corresponding norm in space for the solution. Let's think in terms of the initial data. So we're going to classify spaces in one of three ways. So either they're going to be supercritical, critical, or subcritical. Supercritical means that as you shrink the initial data to small scales, the norm actually goes to 0. Critical means that it stays the same regardless of how you scale, or at least approximately the same regardless of how you scale. Subcritical means as you scale to small scales, the norm actually blows up. And as it turns out, that critical spaces are generally the largest space which improve local L-closeness, or again, these sort of strong but not classical mild solutions. So if you want to construct sort of strong solutions, generally speaking, critical spaces are the largest space you can work in. So you cannot work in supercritical spaces. Generally, the equations should be ill-posed in supercritical spaces. And subcritical spaces, the proof is just easier. Okay, so the most basic result is, well, in vorticity, the L dimension over 2 is a critical space. And some classical work from the 1980s, both in 2D and 3D, show that if your initial vorticity is an L dimension over 2, you can construct a unique local and time solution starting from that initial data for at least some time. Now, in 2 dimensions, of course, we know the solutions will be global in time. But in 3 dimensions, we don't, obviously. So the proof of this theorem is very simple. I actually usually give it in my introductory PDE class or some version of it. Basically what you do, you set up a contraction mapping principle using some suitable space-time norm. And the space-time norm that's most natural is always going to be a critical norm, or the most natural that comes out from the proof. So in fact, these 2 norms that I have on the screen suffice in 2D and 3D respectively. The point is that if you look at these norms, you don't need to worry about the exact balance of time versus LP or whatever. But the point is that when you pick time small, this piece becomes small. So the solution becomes small. So picking time small actually makes the solution small, which puts you in a perturbative regime. So it tells you that no matter how big the data actually is, the data isn't small per se, but no matter how small that is, for a short time, you can treat the equation as a small perturbation of the heat equation. And that's a general principle for proving local opposeness. So basically, the nonlinearity is a small perturbation, and you can close the contraction mapping. Okay, so now what about larger critical spaces? So in 2 dimensions, the critical vorticity space is L1, but the space of finite measures scales the same as L1, but it's not the same as L1. So in particular, you can have Dirac masses. And if you actually start the vorticity equations with initial condition being a point mass, you actually show there exists at least one solution, which is this self-similar Ausen vortex. was actually just this solution to the heat equation. But because of the special structure of the Navier-Stokes nonlinearity, it actually just vanishes on things that are radially symmetric. And so you can prove that this is actually a self-similar solution of the 2D Navier-Stokes equations. And it's really important. So the velocity also does not live in L2. As I said, it lives in a critical space also called weak L2. It's not so important for this talk. And the point is that in any space-time critical, any critical space for the space-time, any space-time critical norm that you assign, this solution will not change size, because it's scaling invariant. So the only thing that controls the size is alpha. So picking time small will not change the size of this self-similar solution. And that's very, very important. So picking time small makes the solution look small in L1, but not in the space of finite measures. And so the whole point is that, well, actually, it's actually just comes down to a density thing. Now, C infinity C is not dense in the space of finite measures in a reasonable sense. And so you cannot get this smallness, essentially. So I'm going to classify critical spaces also into regular critical spaces and ultra critical spaces, sort of extra critical, if you will, for which this small time argument just does not work. Now, nevertheless, in 2 dimensions, one can actually prove, so there's a long line of work starting in the 80s and ending by the work of Gallagher and Gallet in 2005, that proves for the 2-dimensional equations, you can start with vorticity as a measure. And it doesn't have to be small or whatever, and you get global and time well-posedness. So the local and time well-posedness is the only really hard part. So in particular, in the 85, using the same argument that you use in L1, you can basically, well, with some enhancements, you can prove that if your initial measure has only a small atoms, so basically, if this alpha is small, then you can prove you have global opposedness. So that was already proved in the 80s. Then they proved existence of weak solutions for larger data, and then finally Gallagher and Gallet proved uniqueness. Okay, so now let's talk about 3 dimensions, because that's the case of this talk. So actually, it turns out, of course, just by extending in the 3rd dimension, the ascend vortex is also a self-similar solution of the 3D equation. And so what does it look like? This is a vortex column now. So you have at time 0, you have an infinite line of vorticity, and then at future times, your vorticity looks like a Gaussian, all directed in this direction. So the fluid is rotating like this, and it's self-similar spreading outwards. So that's kind of an infinite straight vortex filament. It's the prototypical vortex filament. And it lives also in a critical space. So in 3 dimensions, the critical LP space is L3 halves. So what you get is not finite measures. You get a particular Mori space of measures, which is basically measures which scale like 1-dimensional Hausdorff of a curve, which makes sense. And so I'm going to denote this like this. So what I'm talking about is the initial data, so I always will set my coordinate system like this. So X will be a vector, that's the 2-dimensional plane, transverse to a filament, and Z is along the filament. And so you get kind of a delta function in vorticity directed in the Z direction. And all vortex filaments are in this class of measures. So this is the kind of ultra critical class where the vortex filaments live. So Guy and Miyakawa in the original 89 paper, they proved that if the vortex filament was small in this Mori space norm, so in particular, if this alpha is small, then you have global and time well-posedness. And this, again, it's a contraction mapping argument in a suitable space-time norm. It's just, you can't pick time small, but if you pick the solution small, you still have smallness. So you can close a contraction mapping argument. But what you don't get is any information if alpha is large. So you don't get local opposedness. You have no theorem at all. None at all for alpha large. In velocity form, I think the most famous result in fluid mechanics in terms of global opposedness for small data in an ultra-critical norm is this famous result of Kuk and Kataru, 2002. We studied this. Actually, it looks strange, but it's very natural. Initial data, which is called BMO -1. It's basically saying that the heat extension is in L2 in time, L2 in space, in a kind of scale invariant way. Actually, a nice definition of a norm. If this quantity is small, then you have global opposedness, and you get nothing, or you know nothing if this quantity is not small. Again, you don't get local and time well opposedness in space. That's completely open and probably false. So the velocity associated with vortex filaments is essentially in this space, BMO -1. So it's not an L2, it's not an L3, it's not even a weak L3. It's a little bit better than just general BMO -1, but roughly speaking, lives in BMO -1. Now, a natural question, maybe this is not really germane to the discussion. If you go to even larger critical spaces, then one can prove that you have some issues. Maybe not, yeah, you can have some issues even for small data. So you see, critical spaces are not at all going to all behave the same. So there's at least 3 qualitatively different types of behaviors in critical spaces just for these equations. So, and maybe more in some sense, I don't know. You can get all kinds of different answers. So what do we know about large data ultracritical results in 3D? So we saw in 2D that every initial measure, you get a global smooth solution. 3D, this is not known. So we do know, so this work of Feng and Strack studied vortex rings. So they studied vorticity in exactly this ring directed like this. So this is a smoke ring. So if you've seen someone below a smoke ring, that's exactly what they're producing. They're producing a vortex filament that's a closed loop. And actually you can guess that it propagates forward at some fixed speed related to the intensity. They constructed that no matter how large the intensity is, you can construct a mild solution at least. And Delay and Strack show that you get uniqueness in the axisymmetric class. So these papers are an extension of the 2D papers, sort of like, because if you work in the axisymmetric Navier-Stokes, then it's basically like the 2D Navier-Stokes equations with some additional difficulties later on top. So they basically sent it to the 2D work to study these vortex rings. So those are nice works. Then this other paper by Haojia and Sperak, who studied a different problem, but I think it's important to talk about this work because I think it's really cool, which is they studied actually the existence of large self-similar solutions in weak L3 in velocity form. So these are not filaments. They're definitely not filaments. And so they proved the existence of self-similar solutions, but not their uniqueness, or not uniqueness in a neighborhood of these solutions. And actually, I would say there's very strong evidence that these weak solutions are, that these mild solutions, sorry, are non-unique. And so not that you get like multiple nonsensical solutions, but you actually get multiple smooth, all physically relevant solutions. That's a conjecture. It's not proved yet. 5 years ago, I said it would be proved in 5 years. Well, I'll say another 5 years. Someone will prove it soon, I'm sure. Yeah. Anyway, that's an important example. So now what we want to know is, so vortex filaments, we observe vortex filaments in nature all the time. And these things are clearly have some kind of intrinsic stability. So maybe while general large data in BMO -1 will be highly opposed or whatever, can we say something about vortex filaments for a smooth, non-self-intersecting curve? Can we get local opposedness for these guys for arbitrary alpha? So the answer is actually yes. So that's what we're going to prove, with some caveats to the well-posedness piece. So existence, of course, we have. Uniqueness and stability results we have, but maybe they're not as complete as we would like. So I'll explain what the caveats are. So what we actually can prove is we prove some type of local opposedness. You'll see for a filament actually in a regular background flow, and you can have many filaments as long as they don't intersect, and you have only found many. And it's important to know, as I said, so existence of any solutions was unknown. So it's not just that we proved some uniqueness results, even existence was open. Okay, so the first step is understanding the stability of the Ausen vortex column. So that's the infinitely straight, sorry, the infinite straight filament. Here it's natural, it's not immediately obvious, but you want to set up anisotropic spaces. So we're going to take actually L1 in Fourier, so sort of like a Wiener algebra along the filament, and LP transverse to the filament. And we're going to consider initial data, which is basically of a form, the Ausen vortex plus a perturbation. And the perturbation will be more regular. And so it's important to note this BZL1 is the critical space. So sort of like, if you have a space that scales like L infinity in one dimension, then the transverse guy should be critical in 2 dimensions. So BZL1 is a critical space. So here's the first theorem we have. So if this initial perturbation is finite in BZL1 and this other condition, which I'll explain, so it's a little bit subcritical. You can see our paper for a more precise critical result, but I don't want to complicate it. Then regardless of alpha, and regardless of the size of this perturbation, you get a local and time smooth solution. And the local time smooth solution admits a decomposition, which is the Osn vortex, plus a correction to the core. So omega C sort of corrects the shape of the core of the filament, and omega B is the evolution away from the filament. And you can show that, so omega B lives in the natural space for regular local opposeness in LP spaces. And omega C, as it turns out, this is a natural condition for sort of self-similar scaled solutions to Navier-Stokes, but it's not so obvious. But essentially, omega C goes to 0 in the self-similar frame. So as time goes to 0, the solution becomes asymptotically like the Osn vortex inside the core of the filament, and away from the filament, it behaves just like a regular locally well-posed LP solution. And the uniqueness and stability we get is in this class. So you can prove that any solution of the form Osn vortex plus a small perturbation, in a certain sense, has to be this solution. Yeah, you can see the papers for more precision on that. The proof also yields global well-posedness and asymptotic stability of the Osn vortex for all alpha. So in particular, if this norm is small in a way that depends on alpha, then the solution is global in time and converges to the Osn vortex as time goes to infinity. So it's a global in time asymptotic stability for the vortex column. But small depends on alpha in a way which you can't really quantify that well. Exponential. Our proof gives something like exponential. So the proof is a fixed point. It's not clear that you can use a fixed point for this theorem, but you can. So it rules out the kind of non-uniqueness that is observed or it's conjectured to arise in the examples of Hagia and Vladimir Sprat. But it doesn't show uniqueness of all possible sort of mild solutions in a very general class. So it's sort of halfway between. So it rules out many types of non-uniqueness, but not all of them. So we don't know. So there's another follow-up paper that me and actually an undergrad, a very good undergrad, wrote. He's now a graduate student, of course. But basically saying anything sufficiently two-dimensional has to be this solution, roughly speaking. But it doesn't rule out all possible topologies. So there's still some open problems there. Okay, so how does the proof work? So what we're going to do is we're going to write the solution as the Osn vortex plus a correction to the core plus the boundary, sorry, not the boundary, plus the background, the smooth background of the filament that's supposed to be immersed in. And you have a corresponding decomposition of the velocity fields. Now, the vorticity equation is a transport equation, so it really makes sense to treat it as such. So we're going to divide up the vorticity, the sort of core correction omega C and the background like this, like you would divide up a transport equation. It's a solution to a linear transport equation. But of course, U is coupled to omega. So it's not a linear decomposition. Nevertheless, it's really useful to think of the vorticity equations in this type. And now actually, if you stare at this, you realize that formally, you expect that the only things that are going to be sort of quote unquote ultra critical are terms that are linear. So first of all, the nonlinear things that are nonlinear in omega G disappear. And so that disappears. And so what you expect, things that are linear in omega G, so I think I should just say, things that are of the form omega G times something. These guys, like for example, UC, these guys are the things that should be ultra critical, at least formally, and everything else should at least be small, so they should at least be treated perturbatively. So fundamentally, it comes down to linear stability, or at least that's the first thing you have to prove. So for the correction to the core, it makes sense to work in the self-similar solutions associated with the core. And notice that they're anisotropic self-similar solutions. So we don't take the full self-similar scaling that would be, that would leave the Navier-Stokes equations essentially invariant. We don't do that. That doesn't make sense for a filament actually. So you're only going to take self-similar variables in the variables transverse to the filament. And so what you want to do is you first want to study the linear problem associated to omega C. And this is what it looks like once you move to self-similar variables. So it starts to become a mess. So here LF is the two-dimensional Fokker-Planck operator. So that's what naturally you expect to see popping out when you move to self-similar variables. But again, we moved to sort of this anisotropic self-similar variables. So we have these exponentials floating around that look weird. Okay, so this is the linear equations that we need to study. And we need to understand what happens. Yeah, we need to basically prove that this linear system has this, not really a spectral gap, but something like that. It needs to be asymptotically stable. And okay, so you stare at this for a while, but then you say, okay, well, it's invariant, it's translation invariant in Z. So we can still take the Fourier transform in Z. So if you do that, you end up with this interesting system. And what you can do is you can isolate the terms that have e to the tau in front and terms that don't. Well, we're going to keep one e to the tau term on the right-hand side because it's leading order, comes from viscosity. But then you see these asymptotically two-dimensional contributions. So this gamma here is this kind of sort of vortex stretching piece. So it has a sort of a vortex transport type flavor. And this capital lambda is actually the two-dimensional, it's the linearization of the Euler nonlinearity in 2 dimensions. So these are two-dimensional, this is a two-dimensional Laplacian inverse. And everything else, actually, somehow the Z-dependent pieces has some powers of e to the tau in front, and you're going to move it to the right-hand side. So you say, okay, I have somehow approximately two-dimensional pieces plus something that we're going to treat as a perturbation. And everything that appears on the left-hand side actually has been studied in the literature before. So of course, the linearized 2D Navier-Stokes equations have been studied many times. So in particular, there's some good work by Gillet and Wayne that have lots of good estimates about it. The other equation has been studied a little bit by this one paper by Gillet and Maekawa in the study of 3D stability of the Burgess vortex. But in either case, both have been studied before, and we can pick up where they left off and prove whatever that we need to prove about them. And so in particular, both linear propagators are stable with spectral gaps in polynomial weighted spaces. So you can prove something like this. So actually this vorticity transport looking guy, this guy actually just has a decay estimate with because there's no zero eigenvalue to get the mod out to get the decay. As long as the alpha is not zero. So there's actually kind of like a hypocoercivity of two-tail on that. And in the other guy, the linearized 2D Navier-Stokes equations, there is a zero eigenmode that you have to mount on in order to see the decay. So both of these decay estimates are basically, they come from the special energy structure that you get in the Gaussian weighted space. So exactly how to extend the Gaussian weights to the polynomial weights is actually studied in papers by Gillet and Wayne. Okay, so basically what you have is, in the end, it's not at all obvious, but I'm not going to go into details. You can actually treat all the fundamentally three-dimensional terms as perturbative if you work hard enough. And basically it's saying that as tau goes to minus infinity, these terms are perturbative to the asymptotically two-dimensional terms. But basically what we're saying is that the linearization becomes asymptotically two-dimensional in a sense. And so, okay, then the thing is that the 2D equations are uniformly stable in alpha in a certain sense. And so you get stability for all alpha. Now you get a huge constant here. And actually the proof we have isn't even, don't think it's quite quantitative in alpha, but you can make it quantitative in alpha, and it's exponentially bad in alpha. But you get it. I mean, for each alpha, you get the stability. Now for the 2-bit, now we also have a piece here. Let me go back to the equations. So we have a sort of ultra-critical piece that comes from linear interactions of omega g, but you also have a linear piece here because there's a UG here. And there's a UG plus something here. And so there's another large linear contribution there. And so what you have is actually, you have an advection diffusion equation with a critically singular velocity field. And the velocity field is singular enough such that you actually can't, using direct method, you can't prove local opposedness easily, I would say, even for this linear semigroup. So that actually takes some thought. So what you get is, you're asking about this vector valued advection diffusion stretching equation in 2 dimensions. But yeah, the UG is singular enough such that you don't know how to prove well-posedness with a simple argument, even though it's linear. But if you stare at this equation long enough, you can start to tease out some special structures. So the Z component, you get a nice advection diffusion equation, no stretching. And in the X component, you can actually write down the stretching piece as something that's much more manageable. So what you get is, so this is kind of a rotation. The J is the rotation matrix. So this just causes the fx to rotate. And here, so this is basically saying that the radial component of fx is forcing the angular component of fx, which makes sense if you think about vortex stretching. If you think about linearization of vortex stretching around a vortex, as the flow shears and twists, the vorticity will tip down and stretch out in the direction of the shear. And so you look at this and you say, oh, well, actually, this is kind of, you're not going to get sort of an exponential explosion. You're going to get this kind of behavior. It's like a non-normal growth kind of behavior. And so that's okay. So it won't beat the viscosity, right? So solutions to this equation decay for all alpha, right? Even though you have some growth, some large constants in alpha, but they all decay. And so basically by latching onto the structure and taking optimal advantage of it and getting to work, and also using that, you can actually prove local well-posedness for this equation, which, like I said, actually is not completely obvious. It's too singular. So you need to use that this is a vortex and not some kind of explosion or implosion or something. But okay, we know how to do that. And so with some work, you can actually prove local well-posedness of this system in a class which is a little bit more restrictive than BZL1. You can't quite treat BZL1. We use some kind of slightly stranger class, but it's okay. So if your initial data is a little bit regular, you can prove local well-posedness for this semigroup. And you can prove also these kind of LP to LQ regularization estimates, which you need to close the contraction mapping. You need actually a bunch more estimates than this, but this is just a flavor. But you can do that. And so after a bunch of work on linear problems, the nonlinear problem becomes simple for this straight filament. So maybe I should have said that first. Somehow, once you solve the linear pieces, you get good enough estimates on the linear problem, then you set up a contraction mapping. You have to set up the norms in a slightly clever, not even very slightly clever way, epsilon clever way for omega C and omega B. And you can close a contraction mapping principle with relative ease. It's not as simple as regular local opposedness, but it's not very difficult. So the hard part is the linear treatment. So that handles the case of the infinite straight filament. Now let's talk about an arbitrary filament. And here I want to think about a closed filament. I don't want an infinite filament anymore. So think about a filament shaped like this, and I want to know, can I get local opposedness? So what I'm going to do is I'm going to set up a coordinate system that connects sort of, I want to say, okay, transverse to the filament, I'm going to make this the Z variable, and I'm going to make this transverse variable. So I want to set up a coordinate system that, at least in a small tubular neighborhood of the filament, I can map basically this tubular neighborhood to a cylinder, which is periodic in Z. And flat in X. So I'm going to set up an orthonormal frame along my filament. I'm going to define the mapping in this way, which makes sense. So this mapping is going to be very important because I'm going to use all these anisotropic spaces again, because these are the spaces in which the linear behavior is all naturally studied. And what I want to do is I want to study the equation. So just to recap, I'm studying initial data, which is basically a measure concentrated on this filament, plus some background perturbation, which will be smoother, sort of much smoother in this case. So we don't know how to get sort of optimal regularity for the background, but okay, one thing at a time. So what we can prove is the following, is that for all alpha and for all smooth non-self-intersecting curves, if the initial background is smooth enough, and okay, this is just some space that is just the space in which the argument works. I don't think that plays a very special role. So it's definitely solidly subcritical. Then regardless of alpha or the size of the background perturbation, there exists a local and time mild solution, which is smooth for positive time, which satisfies the following. So it satisfies, if you look inside this tubular neighborhood, if you sort of pull back to this, and then my writing is somehow turned off. Okay, hopefully I will make the rest of the talk without being able to write. That'll be difficult. Okay. So, right, where was I? Right, so if you look in the tubular neighborhood, then in this tubular neighborhood, if you pull back coordinates in the correct way, you have to respect the vector value structure to do that. Then you get the Osend vortex. So that's this first term here. Let me see if I can reset my pen. So that's the first term, and then you get a core correction, and then you have the background piece. And there's a bunch of other estimates that you can prove about the behavior away from the filaments. That all satisfies whatever you naturally think it should behave like. And you have some other estimates as well, but these are the main things. And again, you get uniqueness and stability in this kind of restricted class. So you get some type of uniqueness and the stability of the core correction and the background. Okay, so why is the theorem possible? So I think the best intuition is the following. When you make this change of coordinates, so when you straighten the filament, so you have some kind of curve and you straighten it out, so you sort of like flatten it into a cylinder, the gradient operators all have a bunch of, they all change to be inhomogeneous. And if you actually painstakingly compute out the curl and the Laplacian in these new variables and look at it carefully, you realize actually that the leading order corrections vanish on the curve linearly, like this, like how I've written. But the second order contributions, I'm really sorry about this lack of my pen for some reason. The second order contributions and also, in the Laplacian and the first order contributions in the curl, these guys all vanish to leading order, right along the curve. So that tells you that the curvature effect of the filament, the fact that the filament is curved, is subcritical. So in self-similar variables, when tau goes to minus infinity, when you're studying when you're making that very detailed study of the regularization of the filament, these curvature corrections are formally subcritical and should be treated perturbatively. And basically, general philosophy is if you're trying to prove local opposeness especially for a semilinear equation, and you have reduced it to subcritical questions, then maybe it will be hard, but you will succeed if you try hard enough. My general belief. It's not true about critical equation, not true about critical, and definitely not true about supercritical, but should be true about subcritical. And so, indeed, it took a lot of work, relatively speaking, but in the end, that's how the proof works. So we're going to treat the curvature as subcritical. So it's a little bit too technical to go through all the details. So let me just give you sort of a slight flavoring. And I'll try to focus on intuition because keeping track of the coordinate change and the push forwards and pullbacks and whatever starts to become annoying. I don't want to get too bogged down. So let me just give you a brief flavor of how the nonlinear argument is done. So we're going to decompose the solution as an approximate solution, omega g. So it's no longer going to be an exact solution, but it's going to be our leading order best guess approximate solution, plus two corrections to the core and two things in the background. So I'll explain why I need sort of four, a decomposition of four variables in a second. Well, need is a strong term. I should say why we use them. So omega g is going to be a suitable approximation to what we think the filament will be doing. Since we're going to look at sufficiently short times, the first thing, the fastest thing in the system should be the viscosity. That's an important thing. So actually, omega G is essentially an approximation to the heat extension of filament. But I'm not going to take the heat extension of the film. I'm going to use an approximation. So what I'm going to say is that if you look in the straightened variables, if you look in the straightened variables, I want the approximate solution to be the Océan vortex, exactly the Océan vortex, which, like I said, is not actually heat extension, but it's approximately the heat extension. And now I want to find the corrections to this. So here things get difficult. So what I want is I want to use the linear equations that I've studied. So that means all of these higher order perturbations, all these curvature corrections from the change of coordinates, I want to kind of treat them all perturbatively. I want to sort of throw them all away. So in particular, for example, I want my inner core corrections, that's going to be C1. When you look at it in straightened variables, I'm always going to use eta. I don't declare that anyway. I'm always going to use eta in the straightened variables and omega in the original variables. So in the straightened variables, I want the inner core correction to solve the linear problem plus perturbations. Now there'll be much more perturbations now because of the curvature and because I no longer have an exact solution of the Navier-Stokes equations that I'm perturbing around, but whatever. The most problematic thing actually is because there's second order terms that I have to treat perturbatively at all. And so the way we've chosen to squeak around that is with the outer core correction. And there's more than one reason why we do this, but this is one convenient thing. So the outer core correction omega C2 is something that lives in the original variables. So it's sort of the tail of eta C1. So we sort of have to more smoothly transition from the inner part of the core to the outer part of the core. It's kind of the intuition. So omega C2, actually, we're going to study in the original isotropic variables, not in the anisotropic variables. So in particular, we're not going to use the Fourier transform along the filament, because all the spaces that we use in eta C1 involve taking the Fourier transform along the filament in the straightened variables. Omega C2, we can't do that. Anyway, so the second order error terms are actually going to go into omega C2. You can imagine closing the norms becomes touchy, quite touchy. So yeah, there's a lot of details that I'm going to completely sweep under the rug. So the norms in which we close the contraction mapping, but general filament is much more complicated than the straight filament. But this is generally the idea. So it's like, again, the background piece, we're going to have a piece that's supposed to be studying how the background interacts with the filament, again, near time zero. And this is going to be done in the anisotropic spaces. So in Fourier transform along the filament across some L2 space, two-dimensional LP space. Whereas omega B2 will be working in the isotropic spaces. And then we set up the unknowns like this and close the contraction mapping. It's hard. So transitioning between isotropic and anisotropic norms is difficult because they both want to be critical, scale and critical, but now you have much different regularity properties along the filament than across the filament. And that becomes problematic when you when you actually try to sit down and close anything. So there's a bit of work with several layers of cutoffs and things like that. I'm not saying we did it in the optimal way, but that's, I don't know. Yeah, we got the job done. I'll leave it at that. Now, shortcomings. I would say the biggest shortcoming of the work is that the existence time is way too short to justify any dimension reduction models, like the local induction approximation, if you're familiar with it. So that's the kind of the basic leading order behavior that the filament should evolve on if you can prove that the filament exists long enough and remains a filament long enough. So, what we can prove is that the filament exists and is smooth and looks like a vortex filament for short times. Basically, it doesn't instantly blow itself to pieces, which is not at all obvious because it's exactly scaling critical, large data scaling critical. This is what we succeed in proving, but we don't have an existence time, which is a very good estimate as a function of alpha. I would say, so there's a lot of places where we're not, quantitative in alpha, but the biggest and most difficult piece is treating this self-similar linearized equations. So what you need to do is understand the linearized equations in a more fully 3D way. So we were very perturbatively treating them like the 2D problem. If you want to get to longer timescales, you need to include at least some of the three-dimensional effects, definitely. But that becomes really hard really fast. So even in an easier case of 3D Euler, never mind the singular limit of Navier-Stokes, the linearized ascendant vortex column is a really complicated problem. So there's some great works by Gallet and Smith that came out recently who study this, and their work's really cool. It's really cool. I encourage you to look at it, but even their work is not nearly enough to do what we would need to do. And actually looking at their work shows you that it's a hard problem, definitely, to do like a really good treatment of Navier-Stokes linearized around the ascendant vortex and get good quantitative estimates. Yeah, so that's actually a big challenge to go further, in the existence time. So maybe you can have a completely different argument that, yeah, I don't know. I mean, somehow or another, you're gonna have to get better linear estimates. So maybe you don't need perfect ones, but you definitely need better ones than you have. And that seems to be quite difficult. But okay, well, eventually someone will figure out. We'll see. That's it.
Thank you very much, Jacob.
Thank you for listening.
So are there some questions? Maybe if you can please raise the hand, it will be better. Otherwise, you can just switch your micro on and ask a question. Please, up to you. There's no question. Oh, I'm surprised. No question. Anne-Laure, Bruno, Jean-Michel.
No, I'm here, but it was a hi, Jacob. It was a
Hey, how's it going?
Thanks a lot.
Yes, I have a question.
You see.
Okay, but perhaps I asked already. Okay, hi. That question to Didier Smet some years ago on the vortex and filament vortex, because okay, in the theorems there is a time. Okay, the solution exists in a certain space until that time, capital T. But with filaments, what is nice is that physically there are physical time, very interesting, where when we have two filaments, and it is the time where the two filaments touches, and usually they reconnect, and it is very nice to see. I saw that one one day some years ago at an air show, behind place. Okay, so my question is, do you think that there is a connection between the typical time of reconnection of filaments, the physical one, and the mathematical time of your theorems? Is there a relation?
So I would say not of our theorem, but of the best theorem, yes. So our theorem, I think it's choosing time too short to get to sort of these nonlinear dynamics for now. So we don't really know. Yeah. So I don't think it's not the connect. It's sort of what I think the challenging thing here is sort of instabilities that could build up along the filament just from sort of interacting with itself from a distance or interacting with other filaments. They kind of build up along the filament. And sometimes you see these instabilities in the cores of filaments. I think that this theorem could definitely the existence time can definitely be improved, but it will be hard. But yeah, getting to the time when filaments should start reconnecting would be difficult, but really cool. I mean, actually, that's a really important problem to understand vortex reconnection. But we're far.
Okay. That's problem. Open problem. I understand.
Yeah, good one.
Thank you, Bruno. There is a question by Bian. Please, Bian.
Yes, can you hear me?
Yeah.
Okay. From what I have understood, I think you have a background flow which is more regular than the measure value regularity, right?
Mm-hmm. Yeah.
And then you at some point you say this is stable, the dynamic stable. I want to know that in which sense is stable, like in which space you are considering the perturbation.
Yeah. So right, so it's easiest to comment on in the straight filament case. So let's see. So straight filament case, so for some reason my pen is broken, so I cannot erase this. I don't know what's going on with my draw board right now. So my pen's actually working. See, I can open this thing, but I cannot draw. Okay, so what we can say for this theorem, so the simplest thing that we can prove is that small perturbations in omega 0b produce small perturbations. So small perturbations in the initial background produce small perturbations in the core correction and in the background evolution. So it's Lipschitz stable, and the norms are exactly these norms in 3. And you can add some norms, but these are the fundamental norms. And then we did not carry this out. This is carried out in Gallier-Miguelet's work, and I think it could be extended. So it's actually another sort of partially an open problem that one could study is stability with respect to alpha. So if you change alpha, then you should also be kind of Lipschitz in alpha.
Okay, alpha is constant before. Sorry, alpha is constant before the how to say the concentration measure, right?
Yeah, it's the intensity.
Okay.
So yeah, so alpha large is the hard case, let's say. But yeah, so it should also be Lipschitz with respect to alpha. I think that's provable. We did not prove that. You need to prove a few extra things. That's maybe a good problem for a graduate student, for example. Now stability with respect to the position of the vortex is, even in 2 dimensions, actually, people have not made a very concerted study of exactly in what sense the solution should be stable with respect to the position of the vortex. Certainly in a very weak norm like the Wasserstein norm, it should be relatively easy, I think, but it's not very telling. So yeah, to my knowledge, no one has made a really careful study of exactly in what sense it's stable with respect to the position of the filaments. Sorry, of the Dirac masses, even in 2 dimensions. And in 3 dimensions, of course, we don't have a good study of the stability with respect to the filament itself. That's another good question, because it should be some sense stable to the geometric deformations of the filament. But we'll take some extra work to prove that. I think it's an interesting.
Yeah, I can imagine it's very challenging.
Yeah, it can be hard, definitely.
Yeah.
But
so what do you please? So what do you have? What do you have now? It's like if you make a perturbation in the background flow, then it will be stable, right? The correction of the core, the concentration.
Lipschitz.
Okay. Great.
Yeah, and like I said, I'm pretty sure that a small enhancement over work will yield Lipschitz dependence on alpha as well. But yeah, on the position or shape of the filaments, it could be harder. Definitely, it's something that can be done, but I'm not sure in what sense it's stable.
Okay, I see. You answered my question perfectly. Thank you.
Okay, no, I can see no other questions. So if there is no other question, let us thank again Jacob very much.
Thank you. Thank you for listening, everyone.
Thank you again, Jacob, for your talk.
Sure, anytime.
Have a great day, a great afternoon.
Yeah, thanks, you too.
Okay, bye.